All right, Zoomies, can you hear me? Awesome. Yes, I'm recording. Thank you. You already got beat to it. I know, I gave her crap for it, and I'm not going to give her credit for it, but you got beat to it. So. All right. Did everybody have a good weekend? Anybody do anything particularly fun? Oops, I'm not sharing my screen here. Maybe I should do that so the Zoomies can actually watch class. And take two. There we go. All right. So, just some pumpkin carving and horror show watching. I am the world's biggest wimp when it comes to horror movies and horror shows. So, I've never gotten that appeal. I think definitionally being scared is not a fun thing, so I don't understand why people want to do it. But anyways, all right, so today we're going to talk about correlation by the end of class. If you don't already know why this comic is funny, you should be rolling on the floor laughing with how funny it actually is. Excuse me while I, there we go. All right. But before we get started, what did we learn last time?
About post hoc tests?
Yes. Yeah, Ace and Julie both got it at the same time. So why would we use a post hoc test?
To find out which factors are significant in your multi-factor ANOVA test.
Yeah, so it's not just which factors, right? And so it can also be which levels. And so what we're interested in is saying, okay, that there are, at least 3 groups anytime we're running an ANOVA. And remember that an ANOVA is only going to tell you that there's a difference between, for example, these 3 conditions. It doesn't say which one's higher, it doesn't say which one's lower. It doesn't give you any sort of indication as to what's causing the difference. It's just saying, is there a difference, a statistical difference, somewhere between these 3 groups? If you had 5, it'd be between those 5 groups, etc. And so a post hoc test is going to allow you to start differentiating between the different groups and measuring their significance, right? And so if we do have a significant difference between these 3 groups, we'd run a post hoc and see where does that difference exist. And so why do we do that? Why don't we just run a whole bunch of t-tests against A and B, A and C, B and C? Yeah, exactly. So we run this ANOVA. This is called an omnibus test, an omnibus ANOVA. It's going to reduce the risk of a type 1 error rate, right, a false positive. So again, remember, if we've set our alpha level at 0.05 for every test, in theory, that's saying about 1 in 20 tests are going to give us a false positive. 1 in 20 actually truly negative tests are going to give us a false positive. And so by running an ANOVA, we're helping guard against that, such that we're not going to be running a whole bunch of these paired tests until we've established that there is, in fact, a difference between the groups. Good. Questions about what we covered last time? Yeah. Yeah, so anytime you're dealing with probabilities, you've got a certain set probability that something's going to happen. It may be very unlikely, but it can still happen, right? And so that's just the nature of the probability. So if we set our alpha level at 0.05 and run a whole bunch of tests with that same alpha level, that essentially is saying, there's a 1 in 20 chance that any true negative is going to come up as a false positive, right? So if you think about rolling a dice, you have a 1 in 6 chance of rolling a 6. And so chances are very good you're not going to roll a 6. But on average, about every 6 rolls, you're going to roll a 6. And so that's the same idea behind the probability in the alpha here of if we've set our alpha level at 0.05, that means we've set our type 1 error rate at 0.05. And so about 1 out of every 20 tests we run that are not significant or that shouldn't be significant because of the ground truth of the world comes up significant as just kind of a head fake. Make sense? Good question. All right. So I thought I'd give you a fun fact of the day because tomorrow's obviously the election, and this seems a lot more lighthearted than everything else going on in the world. The 30th president of the United States, Calvin Coolidge, thought it was hilarious to push the emergency buzzer on his desk and then hide when Secret Service came running in. I love that so much. I don't know how often he did that, but I think that is so freaking funny. All right, so today we're talking about correlations. Correlations are just going to be used to establish a relationship or describe a relationship between 2 variables. And that relationship exists when changes in one variable correspond to a consistent and predictable change in the other variable. So as temperature increases, so too do ice cream sales. One goes up, the other goes up. As one goes down, the other goes down in that case. It's important to note, though, that correlation doesn't equal causation. All right? So it could be that from the same ground truth, I see, the number of flip-flops worn correlates with the amount of ice cream consumed. Well, it's probably not the case that flip-flops are causing ice cream consumption, nor is the fact that ice cream consumption is causing flip-flop wearing, but it could be a function of some third variable like temperature outside. So yeah, Evan says like shark attacks and ice cream sales. Yeah, so there's that kind of classic correlation that as ice cream sales increase, so too do shark attacks. Again, it's probably not that people are getting attacked by sharks and then going and dealing with their wounds by eating ice cream, or that eating ice cream then makes you more likely to get attacked by a shark. It's likely that there's some third external variable. There are also what we call spurious correlations, right? Correlations that have nothing to do with each other. You get enough data, things are just going to vary one another. I think there's a website, I don't remember the exact thing, but if you just go to Google and type in spurious correlations, there's a website that has all sorts of these. And there are things like, the per capita cheese consumption in Wisconsin correlates with the age of Miss America, right? I mean, there's clearly no relationship there between those, but they are correlated in that case. And so what you can see here is a representation of data. This line is actually what we're going to call a regression line, and we're going to go over that next time. But you can see that there's an overall trend in the data such that what is that, x-axis, the time to complete the exam in minutes, as that increases, the grade percentage decreases. Right, so this isn't saying that how long you take to finish the exam is predicting or is causing your performance. All it's saying is there's a relationship. It's typically the case that for those who take longer on the exam, we're going to see worse performance. Right? And you can think of causal explanations for it, but it's just describing a relationship. And so if we looked at something like family income in thousands of dollars and students' average grade, you can see that as income increases, so too does the average grade. Right? This is one of the issues with socioeconomic status, right? As students have more available resources, because their family has more wealth to put into things like tutor or being home from work to help kids with homework, or even things just like preventing malnutrition, you tend to get better performance in school, right? And so this would be an example of a positive correlation, and we're going to talk about the difference between those two in just a second. So you can see, you could think about a potential explanation between these two. It could just be spurious, but knowing a family's income, let's say the average family income here of $110,000, we know roughly is going to put the student's average grade at about a 90, right? Not necessarily saying that's causal, it's just allowing us to predict the state of the world. And so correlation typically evaluates three aspects of the relationship between the data. It gives us the direction. We're going to go over each one of these separately. It gives us the direction, the form, and the degree. So the direction of a relationship is measured by plus or minus. Or said another way, by positive or negative. A positive correlation means that the two variables tend to change in the same direction. As ice cream sales go up, so too do shark attacks. As ice cream sales go down, so too do shark attacks. I'll show some graphical representations of this in just a minute. A negative correlation, on the other hand, is that two variables tend to change in opposite directions. So as one variable increases, the other one decreases, and vice versa. Can anybody think of an example of a negative correlation?
Maybe as like the temperature goes down, there are more people watching TV.
Yeah. So as temperature goes down, more people are watching TV, right? Or as temperature goes down, the items of clothing worn goes up. Right? So there's an inverse relationship. As one goes up, the other goes down. As one goes down, the other one goes up. Kenya says, less sleep, higher weight gain. Exactly, yes. And that seems to be a causal relationship, that as the number of hours slept goes down, the frequency, or excuse me, the speed at which people gain weight goes up. The number of cups of coffee I have goes up. My sleepiness goes down. Oh, no, Kenya, I wasn't saying that that wasn't a good example. I was saying that that's a correlation, but that there is also causal evidence for that as well. So that wasn't a bad thing. The important thing to note, though, is that positive and negative don't mean good or bad. Right? There's a propensity to think that a positive relationship is a good relationship. Right? So, well, actually, I don't want to confuse you, so I won't give you any examples. But positive just means as one goes up, the other one goes up. As it goes down, the other one goes down. And negative correlation means as one goes up, the other one goes down. and vice versa. So you can see here an example, relationship between beer sales and temperature. So as temperature increases, so too do beer sales, right? So at 20 degrees, there's not that much beer sale, but at 80 degrees, beer sales go way up. So would this be a positive or a negative correlation, temperature and beer sales? Positive, exactly. That is a positive correlation. On the right-hand side, we have the relationship between coffee sales and temperature. All right, so as temperature increases, coffee sale decreases, such that at 80 degrees, we have a lot less coffee sale than we do at 20 degrees. And is this a positive or a negative correlation? Negative, exactly. Questions about the differentiation between positive and negative, or anything we've covered so far? Are we going to go over causal relationships? So causal relationships are frequently derived from the types of experimentation we've talked about up to this point in the semester, right? And so wherein you are trying to eliminate every other outside variable and you just have one variable you're manipulating, that's an attempt to get a causal explanation. Correlational data, you're typically collecting data from observations in the real world, right? And so you're going out and collecting, you know, how much ice cream is being purchased, right? And there's could be a lot of variation in that. It could be where you are, it could be the type of ice cream, it could be how seedy the ice cream truck looks, things like that, right? And so causal relationships are frequently derived from explicit and specifically controlled experimentation, whereas correlations are typically saying, hey, look, there's a relationship here, and that relationship should be explored in this careful sort of experimentation, right? So you'll see a lot of medical studies. This is actually a really good question. So you'll see a lot of medical studies that will say things like, you know, red wine linked to, you know, longer life or things like that. And so the suggestion is that those who increase their red wine consumption, at least to a point, live longer. It's not the case that experimenters said, okay, let's get, you know, 1,000 people and make 500 of them drink red wine every night and then make 500 of them never drink red wine. It was more the case of, hey, tell me how often you drink a glass of red wine and how many glasses you drink when you drink. And so that would be a correlational study. Does that make sense? Awesome. It's a very good question. And so the most common form, when we're talking about form, is a straight line, or what we call a linear relationship. All right, so we go back here, you can see we can plot the data by that straight line. It's a linear relationship. I don't know if I've got, no, there aren't many examples. So you can have a variety of nonlinear relationships, right? So you could have a relationship that look like this, right? So maybe this is actually the representation of what red wine and longevity looks like, right? So maybe at low levels of consumption, right? And the suggested causal mechanism here is the antioxidants and other things that are good in red wine. But you can see here that maybe at low levels of red wine consumption, the longevity is kind of baseline. As you start to increase your consumption to a point, you increase your longevity. But then if you're drinking a bottle of wine a night, that actually has deleterious effects on you, right? So you could have a non-linear relationship that looks like that. You could have a nonlinear relationship that looks like that. But we're going to be measuring these linear relationships. And all we're going to be talking about in this class are linear relationships. Don't worry about nonlinear relationships. Nonlinearity is higher level statistics. But we're going to be measuring those linear relationships with what's called the Pearson correlation. And the Pearson correlation is essentially going to be a measurement of how close are each one of these dots to a perfect line. I'll show you the equation in just a little bit, but it's essentially saying, okay, let's find the line that best fits these data, right? That minimizes the average distance from each of these data points. And that's what we're going to be doing next class when we talk about regressions. I'm saying let's find the best fit line, and then let's see how closely these data map onto that line. And that is what we call that degree of the relationship. So the strength or the consistency of the relationship. And it's measured by a numerical value ranging from -1 to +1. And a correlation coefficient, which is what we call this degree, of 0 means there is absolutely no relationship. A value of 1 indicates a perfect relationship, such that I can know exactly what your value of y is going to be by knowing what your value of x currently is. Same thing with -1. Very, very, very few things in life are perfectly correlated. So here's some examples. What we have up here is a perfect correlation. You can see each one of those data points falls exactly on that line. There is no deviation from that line. If I know your point on x, I can give you your exact point on y. And would this be a positive or negative correlation in the top left? Negative, exactly. It's a negative correlation. What we have in the top right is an example of no correlation. Right? There is no direction you could draw a line that would seem to fit this data. And if you look at this data is just a cloud. If you tell me where your value else? All right, we're re-recording. All right, here we go. So back to this. I don't know if y'all heard in class, but we were talking about an R of -1 means a perfect correlation in the negative direction, and R of +1 means a correlation in the positive direction. This, again, is an R of 0. It looks like 1, but that's a 0. There is no relationship there. I can't tell you anything about where your values lie based off of knowing your X data point. What we have And panel C on the bottom left is a moderate positive relationship, right? You can see the directionality of these data. You can see they're kind of trending in the upwards direction. So this would be a positive correlation. And if I had to estimate, I would say that this is probably an R of 0.8, we'll say. And so again, it's positive, as indicated by the fact that this is just 0.8 and not positive, or excuse me, not negative 0.8. So it's a positive correlation, and these data points are fairly close to that line, right? Pretty good linear relationship. What we have in D is a weak negative correlation, right? So you can see how a line would fit right through those data in kind of a negative direction, but there's not a lot of closeness between the data points and that line. So this one may be a correlation of, let's say, negative 0.4. Right, so it's a moderate negative correlation.
So you would say either no, weak, moderate, or perfect correlation?
Yeah, I mean, so the label you ascribe is kind of less important than the actual number you get. But yeah, so it would be no, low, moderate, high, or perfect. It's typically the convention, but.
I remember you seeing on the APA exam.
Yes. All right. So to compute a correlation, you're going to need two scores. One for X, one for Y, for each individual sample. There are correlations that allow you to deal with missing data, and there are conventions for when you're dealing with missing data. But for what we're going to be doing, you need a data point for X, you need a data point for Y for every participant, right? So it's the same participant, they have X and Y values. The Pearson correlation requires that the scores be numerical values from either an interval or a ratio measurement. So we'll go over kind of categorical, what's called dummy coding later. But they have to be interval or ratio for a Pearson correlation. So to compute that Pearson correlation, you first measure the variability of X and Y scores separately by computing the sum of squares of the scores for each variable. And so you're going to get a sum of squares X, you're going to get a sum of squares Y. You're then going to measure the covariability, which is to say the tendency for X and Y to vary together, with the equation for SP, and I will show you that in just a second. And once you have that sum of products, that SP value, you find that Pearson correlation by computing the ratio of SP, that value you just got, divided by the square root of the sum of squares X times the sum of squares Y. right? And this notation looks a little weird, but again, that notation is just indicating that you're multiplying the sum of squares x times the sum of squares y, and then getting the square root of that, and then taking the SP value and dividing by that square root value you just found. So the equation for SP is the sum of x times y minus the sum of x times the sum of y divided by the number of pairs we have. So this sum of xy here is an indication that we're multiplying x to y, or multiplying x by y rather, and then adding up all of those multiplications. Right? So we do 1 times 3 gives us 3. 2 times 6 gives us 12. 4 times 4 gives us 16. 3 times 7 gives us 21. And that sum of xy is all of these added together. So our SP here would be 52 minus the sum of x, 10, times the sum of y, 20. That's going to give us 200. Divided by the number of pairs. Or we could just think of it as the number of rows in our data set. So 1, 2, 3, 4. Divided by 4. It's a 4, not a y. Gives us 52 minus 50, or an SP of 2. So now, to get the actual correlation, we take that 2 and we divide it by the square root of the sum of squares x times the sum of squares y. And so the sum of squares x is 5, the sum of squares y is 10. If I put this in, I've got to enable the rotation on the phone. This is a pain. All right, so if I take 5 times 10, that gives me 50. And I take the square root of 50, that gives me 7.07. So now I have 2 divided by 7.07, which gives me 2.8 or 0.283, or we'll just say 0.28. Right? And so is this a positive or a negative correlation? Positive, exactly. Just is that number positive or negative? It's positive. So what this is saying is that there's kind of a weak relationship between these two variables, right? You could actually plot this out if you wanted to, and you would see that there's not really a great line that's obviously going through that value. Questions about this form of calculation? We're going to go over a couple others. Linear or nonlinear? No, but the type of test we did represents that, right? So, so first question of the form. It does not tell you the form necessarily, but a Pearson correlation coefficient is always a linear relationship, right? And so you're always testing linear relationships when you're doing the Pearson correlation. And so that's saying that there is, you know, a 0.28 correlation between those two variables, looking at a linear relationship, right? And so we won't go over any nonlinear relationships because that starts getting a little bit more complex. And your other question was yeah, thank you. Yeah, so it does tell you the degree, right? So this is on that continuum from -1 all the way to +1, right? So 0 is no correlation, and we're somewhere right in there, right? And so it's not really that strong of a correlation. And we're going to go over in just a few minutes. You remember when we talked about R squared as the effect size measurement earlier? It's going to be the same thing here, except now, instead of any other calculation, we're just going to square that value, right? And that's going to give us the percentage of variance explained. And so then you'll be able to see kind of, in a way that makes sense, I think a little bit easier, how tight that relationship is. Nancy says, how do you get 5 as the sum of squares? So the sum of squares is just that same equation we've always been doing, right? So the sum of squares equals the sum of x squared minus the sum of x squared over n. Other questions about this? Ketriel says, remind me where you got 7.07 for the last equation. So 7.07 came from this, right? So I took the sum of squares x, which in this case was 5. I multiplied it times the sum of squares y, which in this case was 10. So that gives me 50. And now I'm taking the square root of 50, and the square root of 50 is 7.07. Of course. All right. So that was one way to calculate correlations. Another way that will give you the exact same answer, it's just a different way of going about it, is with this covariance measure that we're then going to put over the standard deviation. And so the covariance equation is going to be that sum of x times y minus that sum of x times that sum of y divided by the number of pairs all divided by n minus 1. All right, so if I were to write this out in a different way, it would be sum of xy minus sum of x times the sum of y over n all over n minus 1. So it's the same thing. And so let's take this data. Now we've got our x values, we've got our y values, we get our xy values. How do we get our xy values again? Yeah, we just multiply x times y. Exactly. And so we've got our sum of x, we've got our sum of y. And I've calculated out for y'all the standard deviations for these two variables. And so now we can just use that same covariance measure So again, that sum of xy minus the sum of x times the sum of y divided by n, and all of that divided by n minus 1. So 66, that sum of xy down here, minus the sum of x 12, come on, move, there we go, 12 times the sum of y, 20, divided by the number of pairs. So you can see here we have 4 pairs, 1, 2, 3, 4. And then all of that over those number of pairs minus 1, so 3. So this is a different data set, but we get a covariance of 2, just like we've got SP of 2 before. And now when we run it, we take that covariance score we just calculated back here. So covariance XY of 2. We've got our standard deviation of X. We've got our standard deviation of Y. To get that R value, we take that covariance and divide it by sum of squares X times, or excuse me, standard deviation X times standard deviation Y. So 2 divided by 1.82 times 1.82. That's not 182. 182 gives us 0.6. So in this case, this is a medium or a moderate positive correlation. Questions about any of this so far? Each time I get to this point in the semester, some students are freaking out saying, this seems too easy compared to what we did for the ANOVAs. What am I missing? It is a relatively easy calculation, right? So after having gone through the battles that y'all did with ANOVA, you are, yes, you can. You are in a much better position. Which, Ryan, which equation? Okay, cool. I don't know where the hell those gold stars came from. Maybe it's my subconscious giving me a pat on the back for a job well done. All right, so thus, given what we just talked about, the Pearson correlation is comparing the amount of covariability, how much they vary together, to the amount that X varies and Y varies separately, right? How much they vary together and how much each of them vary independently. So again, just to reiterate, the magnitude of that Pearson correlation ranges from 0, indicating no relationship, or at least no linear relationship, between X and Y, to 1, that could also be a -1, indicating that positive or negative perfect straight line relationship between X and Y. Do y'all not see the gold stars on Zoom? There's one right there. Oh, okay. I thought I was going crazy for a second. And now there's one up there. You don't see it? Shut up. You're pulling my leg. They're not on PowerPoint anymore? What the hell? It's a good thing I'm sober, or else I would start questioning my sanity. All right. Oh, good, they're sticking around. So we can also run what's called a Spearman correlation that we use in two kind of general situations. One, measuring the relationship between two ordinal variables, which is to say that X and Y are both ranks. Who can give me an example of a type of research question that who can give me a type of research question that would employ this first situation?
Like with the ordinal,
Yeah, two ordinal data sets.
maybe something to do with the place that others went, right?
Yeah, and so we could do, what's the correlation between your placing in race 1 and your placing in race 2, right? So what position did you get in each one of those? Now we're going to correlate those. And 2, it measures the consistency of direction of the relationship between two variables. And in this case, you would have to convert two ranks before using that Spearman correlation.
So this one is for only ordinal variables.
Yes, exactly. Yep, you only use Spearman, although it's going to look very familiar. You only use Spearman when you have ordinal data.
Why don't you start something?
Oh my God. I've never been somebody who could lucid dream. It's because I haven't been able to like get myself to think, am I dreaming? And then just another one went away. But like this seems like a dream situation. Part of me wants to like think if I can fly here, but it doesn't seem to be working. So, all right, presumably I'm awake and we're not all collectively seeing things. I give up. I give up entirely. This is one of the more strange things I've seen in class. And another one. I literally have no clue what's driving this. All right, well, we're going to continue on. Like nothing's happening, nothing to see here. It's 2020. The AI has become self-aware. All right, so the calculation of the Spearman correlation requires the two variables are observed for each individual, like with that Pearson correlation. The observations for each variable are rank ordered. And note that the rankings for X values and Y values, you guys are very sweet, thank you. The rankings for X and Y values are done separately, right? So you rank from 1 to N for X, and you rank from 1 to N for Y separately. After the variables have been ranked, the Spearman correlation is computed by either using that Pearson formula with the ranked data. Right, so Spearman correlation is just a Pearson correlation, except you will have created a rank order. Or using the special Spearman formula, which relies on the assumption that there are few, if any, tied ranks. All right, so we have two variables. We have X, we have Y. And you can see that these are non-ordinal data as they exist right now. For X, we have 3, 4, 10, 11, 12. For Y, we have 12, 10, 11, 9, 2. And so we then first create our X rank. And it just so happens that these X values are in an ascending order, which is why you have 1 through 5. Somebody always gets tripped on this every semester. It's not just the first data point gets a 1, right? It's the smallest data point gets a 1, the second smallest gets a 2, right? And so instead of, if this were 5 instead of 3 up top here, these X ranks would be reversed, right? And so you would then have 2 and 1 instead of 1 and 2. So it just so happens they're in ascending order in this case. You can see for the Y rank, we give the smallest value again a 1, give the second smallest a 2, give the third smallest a 3, fourth smallest a 4, fifth smallest a 5. So once we do that, we then essentially just discard this original data and rely only on the X and Y ranked data. And when we do that, we just carry out that Pearson correlation, but with this X and, excuse me, Y rank. Questions about that? I don't know the story of Spearman, at least in this context for the Spearman correlation. But every semester, it makes me think that, man, all it takes is a slight manipulation of one person's idea to make yourself famous. I love it. He essentially said, we're just going to do the Pearson, but I'm going to rank them, and then we're going to do our correlation. He is the Google to Pearson's Ask Jeeves. All right. So we can also run what's called a point biserial correlation and get a phi coefficient. And we do this when one or both of those variables is dichotomous. And when I say dichotomous, what do I mean? Yeah, exactly. So two options, right? Yes, no, left, right, up, down. So with either one or two dichotomous variables, the calculation of the correlation proceeds as follows. First, you assign numerical values to the two categories of dichotomous variables. It's typically the case that we just operate in binary when we do this. One category is assigned a value of 0. The other category is assigned a value of 1. Yes, more or less, Kenny. I mean, the binomials are going to look a little bit different, and we'll talk about those in a couple weeks, I think, but more or less. And then once we do that, we just use that regular Pearson correlation once again, that formula, to calculate the correlation. So if you have left and right, it doesn't matter which one you assign a 0 and which one you assign a 1, but you got to do that. And then you can run that Pearson correlation, right? This is also sometimes called dummy coding. This means you're assigning a numerical value to be a representation of a different category. In situations where one variable is dichotomous and the other isn't, and the other one is just regular numerical scores on an interval or ratio scale, we call that resulting correlation a point by serial correlation. When both variables are dichotomous, that resulting correlation, called a phi coefficient, excuse me. So when the data consists of one dichotomous variable and one numerical value, or excuse me, one numerical variable, that dichotomous variable can also be used to separate the individuals into two groups. You can then compute that sample mean for the numerical scores in each group. Right? So if we wanted to look at the difference between left-handers and right-handers on number of Oreos eaten in a day, right, we can separate it such that we can get the average Oreos eaten by left-handers, the average Oreos eaten by right-handers. Right? This in no way is revolutionary. This is stuff that I'm sure you all would have come up with on your own, but you can create that mean separation or that group separation to get those mean differences. Once you do this, that should start to look a little bit like a t-test, right? You could run a t-test on that. And this is why you have that relationship between that R squared and the correlation here. Right, so in that case, that independent measures t-test can be used to evaluate the mean difference between the groups. And if that effect size for the mean differences is measured by computing that R squared value that we've used before, again, that percentage of variance explained, that value of R squared is going to be equal to the value obtained by just squaring that point by serial correlation. Right, you're going to arrive at that same number regardless of how you get there. So again, remember that R squared is just essentially an estimate of the proportion of variance explained in the effect size. True or false, you can have an R squared above 1. False. Why false? Yeah, exactly. Yeah, so there are a couple conceptual ways of thinking about it, right? If R squared is a measure of percentage or a measure of proportion, you can't go over 100% or a proportion of 1. You also, if r squared is truly just the squaring of r, you can't have an r greater than 1 or negative 1, right? So squaring 1 gives you just 1. And so we can go back to our earlier examples, and we had an R of 0.6 for this data, right? That is a correlation coefficient of 0.6. If we square that value, we get 0.36, right? And so that means that 36% of the variance in one variable can be explained by the other variable. So if I just went back to this early stuff in here, let's say that this is in fact 0.8. If I square that, I get an r squared value of 0.64. And that means that 64% of how much these data vary in this little cloud can be explained by the variance along the x-axis, right? So there's still some amount of variability, right? That distance from the line, which can't be explained by x. If it could, that would be a perfect correlation. And the remaining bit could be some other factor. It could be noise in the sampling approach. But again, you can start to see how it all starts to come together, such that if I take that correlation and I square that correlation, I can now tell you what's the predictive power of x and y. Questions about that or anything else we've covered today? Everybody feeling pretty good about it? True or false? Correlations imply causation.
False.
Yes, false. False, false, false. Thank you. Oh, look, we have more stars in the bottom right now. And then, okay, this is getting creepy. Oh, good Lord.
The stars are
all
taking
right.
over.
Right above the N and 0.50, there's a
I think my computer's been hacked or something. This doesn't seem good.
at least it'd be nice.
What in the good Lord's name? Yeah, all right, we're gonna end class so I can figure out what the hell's going on with my computer here. And yeah, thank y'all. See you all on Wednesday.